this revision video for your Edexcel Core Pure 1 Further Maths Chapter 1, which is complex numbers. You've got here the first part of the spec, which is easy enough. It's taken straight from your normal maths. This is your factor theorem. So you start off here, g of 1 is equal to 0, g of minus 2 is equal to 0. So we have square x minus 1, x plus 2. This will give you x squared plus x minus 2. To get the other quadratic, I think I'll just inspect this. So you've got x squared plus x minus 2, x squared plus alpha x, I'll call it, plus 10 to get our minus 20 here. To find the terms for alpha, I'll look at the x squared terms. We've got minus 2 x times alpha plus 1x plus alpha, and x squared plus 10 plus 10 is equal to my plus 6 alpha, then would equal minus 4 plus 2, minus 2. So our other quadratic would be x squared minus 2x plus 10. You'd stuff that into the quadratic formula, and you would get 1 plus 3i minus 1 minus 3i. So now this is where complexities start, because now we've got complex roots. Okay, these are just some key terms that you need to know. So when it comes to complex numbers, your modulus is just the magnitude of whatever you have. That complex number, when you plot it on a graph, the argument is the angle that you make with that line with the positive x-axis or the real axis. So if we had this on a graph, so this is the real axis, the imaginary axis. Let's use our example before, which is 1 plus 3i. Use 1, 3i. So this is our complex number. Our magnitude would be this distance, so that would be 1 squared plus 3 squared, root 10. The argument would be this angle from the horizontal, the real axis, to whatever we have here, be this angle, which you would recognize as tan inverse 3 over 1, which is 71.6 degrees, or which is this the better way to put it, 1.25 radians. His current practice use radians, and this thing right here is called an Argand diagram, which we'll see in the next chapter. Okay, this part of the spec is quite important. It talks about the complex conjugate. So essentially what this is if you've got your complex number as a plus bi, or like we had before, 1 plus 3i, you would have the conjugate being a minus bi, or 1 minus 3i. And you know that real, non-real roots of polynomial equations, they occur in conjugate pairs. So if you have a polynomial, if this is a root, this also has to be a root, like we saw in the example before. We can prove why this happens by just completing the square. So if we use the example that I had back before, your quadratic for the complex roots was x squared minus 2x plus 10. Complete the square on this, get x minus 1 squared minus 1 plus 10 equals 0. 1 whole square, so 9 equals 0. So you have x minus 1 all squared equals minus 9. When you're rooting that, you get x minus 1 equals root minus 9i. No, not minus I, just minus 9. But you'd also have plus or minus, right? So you'd have x minus 1 equals plus or minus 3i. And your roots would be 1 plus minus 3i. Therefore, we've got our conjugate pair, x equals plus 1 plus 3i and 1 minus 3i. Cool. Okay, 2.5 tells us about the modulus argument form. So this just introduces us to a different form of writing complex numbers, and this will be your modulus times cos theta, so your angle, your argument, plus I sine theta. Now this works because I'll show you on my Argand diagram here. So you've got the real axis, your x-axis, and your imaginary axis. So when you're drawing your complex number, let's just use our earlier example, 1 and 3i. This angle, right, we've discussed before, this is 1.249 or 1.5 radians. This thing, what's it called? Modulus, root 10. Is 1 plus 3i. To find our real part, we have to look on the x-axis. So we're going to have to use our hypotenuse, root 10, times cos theta. Likewise, for our imaginary part, the vertical axis, we have to do our modulus times sine theta. And that essentially just proves why we have this form here. That essentially was just a little proof of how we can put our complex number 1 plus 3i into this form. So our modulus, we've said before, 1 squared plus 3 squared, which is root 10, cos 1.249 radians, of course, plus I sine 1.249. Perfect. Okay, now you might be wondering why I've got this plus pi, minus pi and plus pi on this side of my argand diagram. So these are just little tips to help you find the argument a lot more easily. I'll redraw a diagram here because this is really messy. So I've said before that the argument is essentially just the angle from the real axis on the positive real axis to your complex number. So like we have here, just use 1 plus 3i as before, 1, 3, this angle. So that will just be tan inverse 3, which would give you 1.249 radians. That is fine, that we've dealt with that before. What if we looked at it on this quadrant? Say if we had minus 1 this time, and 3i, then our angle wouldn't work. It wouldn't be 1.249, because then the angle would be from the negative real axis. So it's not this angle that we want, it's this angle, right? So the best way to do this would be just to add pi, because these two lines would be perpendicular. Right. Actually, on second thought, these lines being perpendicular actually has nothing to do with it. The reason this plus pi comes about is because tan function is a periodic function, so it repeats every pi, or you might be familiar with 180 degrees. So why is this relevant? So if you had to find this angle, you'd do tan inverse 3 minus 1, which would be just tan minus 3. That would actually give you minus 1.249 radians. You might notice that this wouldn't give an angle in this quadrant, the second quadrant, sorry, but instead it would be this angle. It's entirely wrong quadrant. To rectify this, you need to get to the next possible solution. So you'd have to add pi to this, because we've said every pi the tan function repeats, which would give you 1.89 radians, which would be our argument for minus 1 plus 3i. Alternatively, you could have also had this angle, 1.249, just as pi, which is this whole thing, 180 degrees minus 1.249, and this would still give you the same value. This is probably easier, but using what we talked about for plus pi on this quadrant, minus pi on this one, makes it easier to deal with when you've got difficult arguments, usually around the negative axis. Glad we were able to clear. Okay, now I'm going to walk through a few exam questions. This question, half minus I root 3 is root of equations. The other root has to be half plus I root 3, because they're complex conjugates. Part B says use algebra to solve the equation f z equals 0 completely. So this rules out another method I think would be easier to use, quicker to use. So I'll just run through this quickly. This is x. We can write the quadratic to find these roots as x minus half plus I root 3 and x minus half minus I root 3. So we can also write this as x minus half plus I root 3. minus half minus I root 3. Okay, you'll notice now this is actually in difference of two squares form. So you'd have x minus half all squared minus I root 3 all squared. This gives you x squared minus x plus fourth minus root 3i. So root 3 squared is just 3. I squared is minus 1, so minus 3. So you have x squared minus x plus 3 plus quarter, so that's 13 over 4. And our original equation with this, x z cubed, fine. So this will give us our binomial of term with just x, so we 8x plus, so we 20 to get our 65 at the end. So we can just solve this, set this equals 0, 8x plus 20 equals 0, x equals minus 20 over 8 minus 2.5. Therefore, now we have z equals half minus I root 3, half plus I root 3, and minus 2.5. However, if the question didn't say use algebra, I would be done in literally 2 seconds, 2 steps, because I would just use roots of polynomials. Chapter 4, you'd have sum of roots, minus 12 over 8 minus b over a gives sum of roots. So sum would be minus 1.5. Our sum with our roots before, half and half, that's just 1. So you'd have this minus 1, which give you our minus 2.5. So our total sum would be minus 2.5 plus 1 equals minus 1.5, which is what we have here. Okay, part C says, show the roots on a single Argand diagram. Fine, real, imaginary. So our root is minus 2.5 on the real axis, no imaginary part. And half, call this root 3, this minus root 3. So roots half plus root 3 here. So these are roots plotted on the Argand diagram. We want to show that the roots form vertices of equilateral triangle. Fine. So this we know is root 3, root 3. So this whole side length is 2 root 3. 2 root 3. Find this side length, 2.5 to half is just 3. 3 root 3. That will give you 2 root 3. This would also be 2 root 3. Therefore, we can prove that since all side lengths are equal, therefore equilateral. Cool. Okay, before we get started with this question, let's just rewrite these variables. So you've got z, what's called a plus bi, and z conjugate, this little star here means that it's conjugate. This would be a minus bi. So now I've got that cleared up, we can rewrite this equation as a plus bi, a minus bi. So that's our z times z conjugate, plus 3i a plus bi equals p plus 9i. So this is just sum of two squares. You can say a squared plus b squared plus 3ai minus 3b, because I times I is minus 1, 3b is minus 3b. It's fine. That equals p plus 9i. So let's just collect the real and imaginary terms. A squared plus b squared minus 3b plus 3ai plus p plus 9i. So we can say for certain that 3a equals 9, a is equal to 3. And that's fine, we've cleared that up. Now let's look at the real components. We've got 3 squared plus b squared minus 3b equals p. That's our real terms. So you have b squared minus 3b plus 9 equals p. B squared minus 3b plus 9 minus p equals 0. That's fine. Question says, given that this equation already has exactly one real root, so this already should have alarm bells ringing. We need to consider discriminant. So let's look, b squared minus 4ac equals to 0, because we have one real root. So 3 squared minus 4 b is nothing, 9 minus p, fine, equals 0. 9 minus 36 plus 4p equals 0. Minus 27 plus 4p equals 0. 4p equals 27. P equals 27 and 4. That's fine, but that's not our answer. So we've got this equals 0, right? We can just stuff that in. B squared minus 3b plus 9 minus 27 over 4 equals 0. I won't even bother writing that as an actual number because it's only 5 marks. We've done most of the work. We can just stuff this into the quadratic formula and we'll get repeated roots of b is equal to 3 over 2. Therefore, our complex number, which is what our question was asking, which is z, a plus bi. So we'll have 3 plus 3 over 2i. That is our final answer. Okay, so this last question actually came up in my mock exam and caused a lot of grief within my whole cohort. This is relatively simple once you understand what's going on. I think the formatting threw a lot of people off. This is actually an OCR question. So you've got z bar here instead of z star, as we had before. So z bar equals z star, and they just mean the conjugate. Fine, so like before, z equals a plus bi, z conjugate is a minus bi. 2a plus bi equals a minus bi. Fine. Equals minus 1 plus 7i, 2 plus I. So 2a plus 2bi plus ai plus b equals, yeah, because I times I minus 1 times minus b, it's just b. Like 1 plus 7i, 2 plus I. I would collect the real and imaginary terms here now. So 2a plus b plus I, 2b plus a equals this whole thing, 2 plus I. Actually, to get this into a real, like, easy to use format, I think it would be good to realize this formula, which is something I've realized now is I haven't actually covered. So the process for this is just similar to rationalizing surds. Minus 1 plus 7i, 2 plus I, times here, like we have in surds, you'd reverse this sign. So it'll be 2 minus I up here. Okay, so this just becomes 5. On top here we have minus 2 plus 14i plus I plus 7. So it would give us 5 plus 15i. So that is just 1 plus 3i. Fine, that is perfect. Because now what we have here, 2 plus b, 2a plus b plus, let me write that's a plus 2b equals 1 plus 3i. What we have here is just simultaneous equations. You have the real component and the imaginary component. 2a plus b equals 1. A plus 2b equals 3. Okay, now that we have this simultaneous equation, I personally just stuffed it into the calculator. This is further maths, so I don't think they'd bother giving you marks for a GCSE simultaneous equation. So this would give us minus 1 over 3 and 5 over 3. So that's our A and B. Okay. And the question asks for Cartesian form. So we'll have to write this as coordinates. So for minus 1 over 3, 5 over 3. That is our 7 marks confirmed. The final part of this question asks us to give this in modulus argument form. So we've done this before. I think first let's find the modulus. That would be minus 1/3 squared, 5 squared, which gives us root 26 over 3. That is our modulus. For argument, let's plot this on our Argand diagram. Minus 1/3, 3, 5 over 3. So it's like the situation we had before, right? So we've got arctan, tan inverse, 5 over 3 over minus 1 over 3, which is just tan inverse of minus 5, which will give us minus 1.37 radians. However, like we said before, that's this angle. That'll be this angle, not what we have here. So we'd have to add pi to this to get 1.768 radians. Therefore, our full modulus argument form would be root 26 over 3 cos for argument 1.768 plus I sine 1.768. That's our final. Great, that's it from me. Hopefully my random ramblings all made sense.